today's topic. So we will look at crash recovery. To be honest, that's the most difficult topic of the entire lecture. In some sense, also the most interesting topic because it binds together many things we learned so far. Yeah? So maybe that's like kind of the culmination project, the master project in a way of the lecture, because many things you will see will reappear. And yeah, so so that's the agenda, that's where we are currently. And the main question we will be tackling, we alluded to that multiple times already, is how do we make a system robust against software and hardware crashes? So if anything goes wrong in the system, what do we do from the point of view of a database system? And let's first look at the different scenarios, error scenarios that may appear in such a situation. So what may go wrong? The main typical thing that may go wrong is a power failure, of course, for whatever reason. Typically, servers are secured against that. You have a universal power supply, so that's basically a small battery. Yeah, you put in front of the electricity plug, and if there's a power failure, the servers are protected. These devices also protect servers against variations in the voltage and in the power that comes from the circuit, from the power plant. So many things you can do, but still power may fail eventually. And then the question is, what happens with the database? What in particular happens with the state of the data in your database? Just to think about, I mean, main memory failure, for instance. Yeah? You modified some data in one of the pages on in your database buffer, then the power goes away and all your changes are lost. So what do you do with that? Yeah? Maybe some pages were already written to persistent storage, others not. So what's the state of your data, in particular with respect to ACID? Yeah, then all these kinds of disasters, fire, flood, earthquake, tsunami, burglary. So simple case, someone steals your server. So what happens? Yeah? So there was a famous case a couple of years back on a guy who was very proud about his backup strategy. So he had a laptop with 2 external hard disks. So we had like 3 copies of all of his data. Yeah, but then someone broke into his house and stole all of it. Yeah, the machine and the 2 backup copies. So that's kind of stupid. Yeah. So you should always have a copy in a different place, in a different geographic place, to avoid these kinds of scenarios. Yeah, yeah, the janitor's dog pees on the server. That's another scenario. That's, yeah, you get a short circuit. Hardware error, so we talked about that, hard disk crash. We talked about RAID, how RAID can help in those scenarios, but yeah, even the RAID system can fail. Other parts of the hardware may fail, memory may fail. Of course, there are all these correction codes, correction mechanisms that can cope with certain types of failures, but if there are too many errors, then you might have an hardware error and then you may lose data. The same applies for software error. Yeah? No software is perfect, so maybe due to some particular state, due to some particular thing you do in your software, all of a sudden you run into a state of the software that's not defined, was never tested, boom. Yeah? So what's the state of your data? Yeah, and if you think about ACID, so what does it even mean? I mean, which of these ACID properties are affected in this scenario? Yeah, atomicity, obviously. Yeah? If you're in the middle of a transaction and then you have a power failure, well, you may be violating the ACID property, obviously. Same holds for consistency. Yeah, if the data is not consistent yet, may be violated as well. Isolation is a different story. That's not so much a concern here in what we're talking about today, but durability, obviously. Yeah? So if the database system told you, hey, I committed that transaction, I told you, yeah, then the database system must make sure that it never loses those changes, never loses the data. Yeah, but if the database system only had the changes in the main memory database buffer, but never written to disk, that guarantee can't be upheld, yeah? So the data is lost. So how does the database system do that? That's something we will be looking at. Yeah, then you can classify errors into different categories. So one is the easiest to handle with is a local error. So that's an abort in an application program. You know, as you may know or may not, I'm not sure, when you start a transaction, you can always abort the transaction. So basically the user or the application sends an abort command and then the transaction is aborted. And then you must make sure that the changes, if it did any changes to the database state, are not persisted. Or you have an abort that may, if you remember, we had that in the undergrad lecture. If you have deadlocks in the system may decide to kill some of the transactions, and which means it aborts some transactions. And again, you must make sure that those transactions don't leave a trace in the system in terms of that they change the database state. Huh? Yeah, so what you do here in the database system is basically a local undo. So if there were any changes done by non-committing transactions, you must make sure they don't get persisted. Huh? That would, because if they got persisted, that would violate atomicity and durability. Yeah, here's an example. So on the x-axis, there's a timeline here. Yeah, and we have two transactions running. This is, let's call it T1, let's call it T2, whatever. Yeah, and so the green one committed at the time when the abort. So the green committed. Yeah, that's what I'm telling you here. And the abort was only done within this transaction. So abort doesn't mean that all the running transactions get aborted. Just it's a user command you send to abort your ongoing transaction. And then you must make sure that whatever was done by this transaction mustn't be persisted. Yeah? However, this transaction is not affected. If it committed, it must be persisted. In other words, it must become durable. Yeah, loss of main memory, that's a bit more difficult if that happens. So that's a dirty page problem. Yeah? So there might have been dirty pages in the database buffer, and they are lost. And the problem here is that dirty may mean different things. That may be dirty by changes from transactions that committed, or dirty from transactions that didn't commit. Yeah, so there are valid changes and invalid changes at the same time on the same page, potentially. Yeah, but they were never written down to disk, so that's a problem. Yeah? Still, you want to have the database system to be able to be restart. Yeah? So we will have two tasks in this scenario. That's an undo and a redo. So if there were any changes done by a non-committing transaction, those changes have to be removed from the database state. That's the undo. Yeah? So undo everything a non-committing transaction did. And redo is the opposite or the inverse, if you want, that makes sure that all the changes done by committing transactions are actually persisted, are actually become durable on the store or in the store. Yeah? Those are two very important steps we will be looking at later on today many times. Yeah? Just some terminology. Those non-committing transactions are also called the loser transactions. They lose. They never committed, they lose. Whatever they did, their changes are removed. And the committing transactions are called the winner transactions. They committed at some point in time, so whatever they did, that must be made durable in the store. Yeah, loss of main memory. Here's an example. So two transactions, green committed at this point in time. So as the database system said, yeah, I committed it. Whatever that transaction did, it must become durable. However, this guy here, yeah, it was right in the middle of doing stuff when the power went down. That's this line. There was a power failure. So we must make sure that whatever changes happened before the crash must not be persisted in the database system. That's very important. Otherwise, we violate ACID. Yeah? So that's a typical main memory scenario. Yeah, and then things get more severe. So what if you not only lose main memory, but what if you lose external storage, external memory, your hard disk? So that's a problem. You still want to be able to restart, but then, hey, on what exactly if you don't have hard disks anymore? So let's hope you have a copy of your database filed somewhere in a remote location. Maybe, let's hope it's not that outdated, not from last year, but maybe just from yesterday. But if not, you're in trouble. Yeah? So in a database that keeps really important data, yeah, where you really have a problem when the data gets lost, you have to have a replication strategy, meaning that it's not okay just to store your data locally on some disk. You must make sure you also store it eventually to other disks. somewhere in a remote location. That's very important. Otherwise, if you have a system like that, a situation like that, yeah, you actually lose your local hard disks, you lose your local storage, then, yeah, data is gone. Yeah, and that's even more involved. Yeah, and that's also something we look into this week's assignments is basically you have these things in any kind of software, what I will be talking about here. So you would have seen that in undo functionality in any application. You did something in whatever, Google Docs or an image processing application, and you want to undo what you just did. Yeah? Then you hit undo. That's okay. And then there are basically applications that only allow you to go one step back, and there are other applications that allow you to go back till the start of the document, which is really cool. Yeah? There are even applications that allow you to insert operations in that log of operations at an arbitrary position. Yeah? That's a nonlinear undo functionality then. And in the exercise this week, we will look at that because it's very similar to what I'm explaining in the database context. What's done in the database system, you could use the same techniques when implementing undo functionality in an application. Yeah, and of course, backup copies is something you also do with your files, hopefully. Yeah, that's related, of course. Yeah, a backup, we would call it a snapshot. Like a camera taking a snapshot, taking a picture of something. A snapshot means, okay, whatever the state is of the data, whatever the current state of the database, I take a snapshot of that. And I make a copy and copy that snapshot somewhere. Yeah, so that's the same thing as doing a backup. We call it snapshot. I can write it out, a snapshot. Yeah, versioning in all its flavors, be it Git or older systems like SVN, or I mean, what many people do on their file system is, yeah, they do whatever cv.pdf, yeah, then they change it and save it to cv2.pdf, yeah, and then it's cv2 adjusted PDF, and cv2 adjusted minor and so forth and so forth. Yeah, that's basically versioning using the file name, and every file is a snapshot. Yeah, then they also have these features in what's called journaled file systems. So journaled file system, if you understand today's lecture, you will understand journaled file systems because a journaled file system is like databases, but not that cool. Yeah? It's just a simpler version, only looking at the metadata. Of course, we always look at the entire data, but what journaled file systems do is when they crash due to a power failure or something, when the file system is started up again, it can reconstruct the structure of the file system and all of all the metadata automatically. So that's the same thing as we are doing, but we do it for all data today. Huh? That's really cool. And database people did it before. Those guys in operating systems did it. Yeah. Sometimes we also steal stuff, but I think this time the operating system, file system people stole it from databases and didn't do all of it, what we are doing. Anyway, yeah, then that's one of my favorites is do not switch off messages. You see that sometimes when you install software, in particular on the operating system or bootloader or on a level. So what happens is you install some software. It also happens on smartphones, by the way. And then while installing, there's a message, oh, please do not switch off. Please do not disrupt the power supply, blah, 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 blah. Yeah? No, that's bad. That's a bad implementation by definition. The idea is really whatever happens, the system should be able to survive that. Yeah? Even if you install a new operating system, even if you, whatever you're doing, at any point in time, the system should be able to get back to a consistent state automatically, given that the hardware then is okay, not broken anymore. Okay, but if the hardware is again broken, it will still it will crash and try to restart again, restart until it gets over that hardware problem. Yeah, but that's an indication of something was done. Yeah? That's not what we aim at. We really aim at, no, even that should be possible in any situation. So today we will first look at some preconditions you need to allow a system to do something like this. to be able to recover. And for that, the first thing we have to look at is logging, stable storage, and I don't know how to pronounce it in English, it means write-ahead logging. So let's look at that. So when you look at a database system from a 10,000 feet perspective, it can be depicted something like that. I think we had that somehow. There's a user, there's storage, we have a store, we have an indexer, query optimizer. There are many more components you may identify, but that's one way of seeing that. And previously we had this kind of storage, persistent storage, and now I'm adding on the same storage layer a second type of storage I will be calling stable storage. That can be a different hard disk, it can be an SSD, it can even be a remote hard disk, whatever. I'm just calling that stable storage. And the idea of that stable, so here's a more idealized picture of that. And the idea of that is, it gets even more idealized. No, okay. you can't abstract this any further, right? I mean, then we would have a black screen or something like that. Okay, so we have a store and we have a stable storage. Yeah? And so how does logging work? So the idea, it's a little bit like, if you remember, a pirate sailing the ocean, and then he has a logbook. Yeah, and every day he writes in his logbook, oh, today we saw the monster, and today we hunted down the whale, and today 2 people drowned, and stuff like that. That's the logbook. So the pirates wrote, I don't know, 200, 300 years ago, people wrote it, the captain wrote it in the logbook. Yeah? So this is a major events that happened on that day. I'm not sure whether captains are still doing that. It's the same idea here in databases. Yeah? So basically all the actions that are being sent or the change operations that are being or shall be executed by the database system, we keep it in stable storage. Yeah? That is the idea. And let's go through some less abstract examples on how that works. And I will use a different analogy now, that is when you publish a book. So assume I wrote a book on databases. I didn't do that, but assume I wrote that book and it has a first edition. Yeah, and now eventually people start writing emails. Hey, there's a typo actually on page 23. Yeah, you wrote database rather than database, so you should rather fix that. So I record those changes here in this file. Yeah, that is in this world, as explained before, that's stable storage. Yeah? But I don't, if you go back, what I also do in this world, or in this example, is I actually do 2 things. I record the change, so I keep the log entry, the pirate is writing it down in his logbook, but I also perform the change in the book. So I publish a new edition of that book, if that were possible. Typically it's first, second, third edition, so I'm saying it's first edition, or 1.first, whatever. Yeah? And so for every change that comes in, basically, here's a second change, I publish a new edition of the book. And that's rather expensive. Yeah? Publishers don't like that. Yeah? If for every typo you publish a new edition of the book, that's too expensive. At least it was back when books were published on paper. Yeah? Printing it out again, bringing it to the bookstores. Today it's a no-brainer, because if the book is published, do you even know that books were printed before? Have you seen this with paper and stuff? And thumb, yeah, okay, I have an idea what I'm talking about. Yeah. So, I mean, you didn't, when we had the drawer with the card boxes, you said, hey, what the heck is that, right? So I have to check whether my analogies still work. Yeah? Okay, so you've seen a printed book. Yeah? So the pain is really big if it's a printed book. For electronic, not so much. Yeah? Okay, so on and so on and so on and so on. So message is you do those changes on both places always simultaneously. Yeah, let's skip over some of those slides. Oh, that's really a long example. Yeah, and when you do that, so basically this could be, on the right, could be considered a log. The log of the changes you did to your book. And now we will see how that maps to the database world. So the database system also keeps a log, and the log is kept on stable storage. hopefully. When you install a database system, typically it's not, everything is kept on the same file system. There's nothing that's marked as stable. But the idea is that all the change operations you write down. So whenever there's an insert, update, delete coming in, you write it into the log. How exactly we will come to later on. But the idea is whatever might have changed your database system, you write a small record to the log, and the log is a file that's append only. You always add it to the end, like in the logbook again. You write, okay, there was an insert on table tralala, key, whatever, write it down. There was a delete on blah, blah, you write down, write down, write down. So you got a long file with all these change operations. And that has an interesting application because actually if you do that and you keep the entire log, the log becomes the truth. The log is a database. Are you sure you understand what I'm talking about? Think about that for a moment. All the change operations are recorded without changing the state in the actual tables. I just keep it on a high level, like insert, whatever. I could write insert and table foo, key 42, and then a new tuple or something like that. That's something I could write in the log. And then another one, another one, another one, without changing the actual state in the tables, however they are represented, being column, row, store, whatever, whatever, whatever. Yeah? So all the change operations, all the data is available in the log, which means the log contains the entire truth. And if you decide to additionally put that data also in tables, that's your decision. It's just an optimization. Because if you think about that, if you now have a database that only has a log and you do query processing on that, that's really, really painful. That's not going to be efficient. You have to parse all of those log entries. So it's a good reason, there's a good reason for putting this into tables. But in terms of the information contained, the log is a database. Yeah, this log can be read and written sequentially. So that typically leads in installations to the idea that the log uses a special very fast hard disk or very fast SSD. Yeah? Fast with respect to sequential operations, because for certain operations you have to read large portions of the log. You get versioning for free from the log. So typically when you send a query to the database system, you send something like select star from whatever, but certain database systems allow you to add to that an as of timestamp. Yeah, as of yesterday, as of last year, as of tralalala. So like in Git, you can retrieve older versions of the data from your database system, and that is implemented through the log. Yeah, with the log, you can actually, okay, then it was inserted, then it was deleted, updated. You can restore the old state. You restore the old state of whatever table is mentioned here. Yeah, it's a natural extension point for distributed databases. So we looked at distributed query processing last time, but when you replicate data in a distributed system, you can also use these logs to distribute changes. Maybe we'll go into that a bit later. Just I wanted to make sure to mention that. And fifth is also, I mean, those are like in brackets, right? It's not just, I wanted to mention that. If you ever heard people talking about blockchain technology, not in the Bitcoin sense, but in the permission blockchain sense, it's a way different thing from the blockchain currency stuff. People will talk about ledgers. Well, guess what? It's the same thing as a database log, just a different term for that. It's really the same thing. Yeah, so that's a sequential file, sequential read and write operations on a separate storage area, which is called stable storage. So how does logging work? So logging can again be described along the lines of the book. So we have a current edition, and that's a file that can be read and written. So you can read stuff from the current edition and you can write stuff to the current edition, and the changes are just kept in the log file. And one important thing we always have to make sure that that things are implemented like that is called write-ahead logging. And that means whatever you do, always make sure that first you append the change operation to the log, and only then you change it in the store. And that is in particular important when you persist. So it's not allowed, certain situations are not allowed, and we will go through different situations in a moment in detail. Yeah, so write-ahead logging means you first write the log ahead. You first write the log, and then you write whatever you did to the store. That's very important, otherwise all algorithms I explain afterwards will break. So that's a precondition. Yeah, and just a reminder, so here's a database buffer that's organizing pages between main memory and hard disk, and we will use that again in a moment because we have to be careful when implementing a database buffer if we want to make sure that write-ahead logging is respected. Therefore, I'm now writing it with the two layers. So the store has data on those two layers, maybe a page here that is a new version of a page it read from disk, and the same holds for stable storage. So you have to be careful what was persisted and what not. For example, so let's assume that is our initial situation. So we have edition 1, the first edition of a book, and we have it in flash or on the hard disk, whatever, and in main memory. And now you want to do changes. So how do you do changes in logging? Yeah, you record the change in the log file. Here it's only in main memory. It's not persisted yet, as you see here. Yeah, only in main memory. But you don't touch anything in the store. Yeah, just keep the entry in the log. And the log is for the moment just in main memory. Okay? Eventually, you force a log entry to disk. Yeah, now it's written to disk. And that is the point in time where the database system is allowed to say, hey, I committed it. It's okay, you can go on. I committed your transaction. So if that is, if this is reflecting a single transaction, there should be a commit entry. We will get to that later on. Yeah, but if that change ends a transaction and you flushed it to disk, then flash is flash. That's from Queen, right? It's a typo. Okay, you flush it to disk. Yeah, I think that's kind of correct. Wow, I should fix that. Yeah, all right. So at that point in time, when it was written to disk, the database system is allowed to say, I committed it. Again, notice we didn't touch the store yet, so we don't care that is a message. It only counts what's in the log. What's in the store, who cares? No one cares, really, no one. Yeah? Yeah? If you understand the log, you don't have to care about the store anymore. Store is just for query processing. Who cares about that? We did that 2 weeks ago. Yeah, and what you then do, however, eventually you create a new edition 1.1, which means whatever changes you record in your log that weren't reflected in the store yet, now you change them. And you see it here, the change is only done in main memory. On hard disk, you still have the old edition, as you have two versions of the same thing. Yeah? Only eventually then, the new edition will also be written down to the database store. Yeah, so there are basically four places how it trickles in that hierarchy. First on the right, main memory and flash disk, hard disk, and then here afterwards, main memory and hard disk in the store. And that is the order you have to maintain at all costs. That's very important. So here's another example of what you could do. Same situation. We start again with the first edition here. The log is empty. Yeah, no entries yet. So what could happen is, okay, you have a log entry. That's fine. Then you create a changed version of your data in the store. Is that okay or not? Yeah?
It should be okay. Yeah.
Why?
Because maybe you have a query that wait for these changes to compute another change.
Mm-hmm.
And you want to make it faster, and then as it's not committed to hard disk, it's okay.
Yeah, other ideas? In favor or against? Is it okay or not? Maybe you? Yeah?
Yeah, well, as long as we don't persist this change to the hard disk, when the power goes out, the log will be consistent with the
Yeah, great. As long as we don't persist it to disk, So what is the state of the database system at this point in time? Yeah?
I think this transaction not yet committed.
Right. The transaction basically doesn't exist from the point of view of the database state, because in the log, there's no entry on disk. It's just the main memory. You could argue, yeah? You could also argue the other way around from the point of view of the database instance that just did that. Well, it will see that log entry in its main memory, so the state from the point of view of that system is the main memory version. Okay, but the point of view from assume a power failure, the state is whatever is on persistent medium. Yeah, so two truths you could interpret here. So this is okay. Yeah, that's absolutely okay. Yeah, then here you see the log entry is forced to disk, to the log disk here. Totally okay. That's respecting write-ahead logging. And then afterwards, you do the change here by writing it to the database store. That's okay. That's respecting write-ahead logging. So let's do it wrong. So again, same situation. First edition is the start. We have that log entry. Now we change it here. That's also okay, all fine. And then we write it to the store. No, that's wrong. That doesn't work because here we haven't written it down yet. Yeah? That's violating write-ahead logging. Yeah, here it's only forcing it afterwards. That's doesn't work. So the principle, to summarize, is when committing a transaction in write-ahead logging, you first force the log entries to log disk. Then you write the change pages to the disk store. And that has an implication when organizing the database buffer. Yeah? If you remember, the database buffer may have a background thread that writes out dirty pages. Do you remember that? Yeah, there may be a mismatch of the pages on disk and the pages in the database buffer, which were changed frequently. And did I mention that background thread? I'm not sure. No, doesn't look like. Yeah? Okay, so we do that. So basically, when you organize your database buffer, how would I do that? Yeah, so you have all these slots for pages in the database buffer, representing data on disk underneath. There's one missing. Okay, so if that is your disk, and that is, do you even see what I'm writing? Hey, cool. Okay, and this is your DB buffer. Yeah, and then if you have here A and load it here, eventually you modify it, yeah, have B, load it here, you modify it. What you may do in a database buffer is you create a thread that writes out dirty pages back to disk, yeah, to make sure that you don't lose that much data in the store. Yes, you could have a thread that looks at the dirty pages and just writes them out, pushes those changes back to disk eventually. Yeah, that's one way, that's an optimization you can do in a database buffer to not have too many dirty pages. However, you have to be aware that when doing that, when forcing a dirty page out to disk, you now have to make sure that you still respect write-ahead logging. In other words, you write all the corresponding log entries to your log disk. Yeah? So if you wrote out blindly all those dirty pages without writing out their associated log records, you would be violating write-ahead logging again. Yeah? Understand what I mean? Yeah, what we did before was basically from the point of view of a transaction. Here in this example, if we go to the correct example, something like this. Here, yeah, if I write down, here the write is basically triggered by the log, and then eventually you put it in the store. Now it's the other way around. I'm in the database store. I have some changes here. I want to write them out. And you may only do so if you make sure that all the log records that belong to that page, that reflect changes that were done on that page, are first written out. and only then you are allowed to write down the dirty page back to the database store. So it's the same idea. It's write-ahead logging. First, write in the log. All the changes that happen in the system are first to be written in the log and then in the buffer, yeah?
I was just wondering if the flushing of data from main memory to hard disk in the stores section would also be logged.
So if you flush,
For example, like you say this part of the log is already at hard disk.
but then, okay, so you flush some of the entries and then you write next to entry that I flushed it.
You would write the first edition to the hard disk, and then you say in the log it was written to hard disk, so that you could recover the state from the logs.
Yeah, but then what is the state? Okay, but then you rely on the state of your database store or not? Is that the idea?
I was just wondering if you have the logs, but you don't know what the actual, like what part of the logs is already at hard disk level.
Okay. No, the
You could recover it if you didn't know what is recovered and what not.
No, the contract for the log is always if you flush something to the log, everything before that wasn't flushed yet must also be flushed. Maybe I didn't say that. Yeah, so it's an append.
Like but you can, you can only update the log, but not update the store, yeah?
Yeah.
And then you couldn't, at some point you didn't know what is in the store and what not.
Yeah, but I don't have to know.
I thought you want to recover the actual data based on.
Yeah, but we will get to that, how that works. So basically, you will see how that works in a moment. Yeah? So of course I want to recover the store, that's right, but we need some more details to explain that. Yeah? So for the moment, it's just how we log and how we write those log entries. Okay, so it boils down to this sentence. Yeah? The version in the log is younger or equal the version in the persisted store. Yeah? Whatever you see, it's more recent in the log than in the persistent store. Maybe the same version, but it can only be younger and more recent in the log versus the persistent store versus persistent log. Yeah, let's look at how do we log. There's multiple ways on how you organize a log. So the first is called physical logging. There are three different ways, there are more, but three major classes of logging. One is physical logging. And the idea here is that you log states or byte images. And there's a before image that contains the state before the change was performed. And that's, again, like a snapshot of the bytes, of the state of the bytes before you apply the change. Yeah? Then you do the change on the page, and then you have an after image that's a state of the bytes that were changed as of after the change was done. Here's an example. So assume we have this page and we want to change this from key E to CA, yeah, to fix that typo. So what we record in the log is an before image and an after image. Yeah? It could be done like that. You could do it differently, basically saying, okay, at position byte number 367, there are 2 bytes that were changed. And the before state of those bytes was key E, and the after state of those bytes was CA. Yeah, that would be physical logging in a database. The other extreme is logical logging. And that's, in this scenario, high-level operations are logged. And high-level may even mean a SQL operation, a SQL insert operation, a SQL whatever change operation might be logged. There would be one way of doing that. So here in this scenario, to reflect this change for this typo, you could log it as follows. Yeah? So maybe update, maybe that's a key here, yeah? The primary key in the table. I just wrote it down here to explain the 0, saying, okay, the old value was this one and the new value was this one. That would be the high-level operation. And notice that there's no information about the page contained in the log here. There's no 42 here. It's not there in the log, whereas in the previous version, here there was an entry saying, okay, on page 42, at byte position, tra-la-la-la-la, before was that and after was that. So this means a physical operation, a physical logging operation is always with respect to a page, whereas a logical logging operation doesn't matter which page it is on. Yeah, that's an important difference. And yeah, the third class, it's in between physical and logical logging. That's called physiological logging. That's like logical logging, but the log entry may only affect a single page. Yeah? So here, basically, you prefix your this is a logical operation, but you say, no, this must be done on page 42. So the logical operation is restricted to a particular page. That's called physiological logging. Yeah? Those are the three classes. And there are certain performance trade-offs that play a role. And you can differentiate disk-based systems versus main memory systems. So why do you do these things? Why do we have different classes of different types of logging? Yeah? And basically, you see that when you think about the log size. Yeah? How big is a file you're writing? And that is depicted on the x-axis here. So basically, the size of the log pretty much determines the I/O time. Yeah, it's a linear relationship. Yeah, if you scan the log file and the log is gigabytes and petabytes big, then it may take a lot of time. Yeah? Versus on the y-axis, I depict the log entry processing time. In other words, okay, I find the log entry and now I do something with that during recovery. How long does it take to do whatever is described in the log entry? And if you think about that, a physical entry, like applying, that's basically a memcopy thing, copying some new bytes to a specific memory region, that's super fast. Yeah, it's really easy. Whereas when you do something like logical logging, it may boil down to, oh, where exactly do I have to update? Where do I find this key? I have to do an index lookup, and then eventually I find the right page. And then on that page, I do that change. That's much more work typically involved for executing an operation that's written down in a logical log record. And that is basically what you see when you have a disk-based system. So physical log records are relatively fast to execute. Yeah? So it's basically here on the y-axis, whereas logical things described in those systems may take a lot of time. That's much more expensive. However, when you make the transition to a main memory system, things change dramatically. Yeah, so before, I mean, in this world, we are in minutes. Yeah, could be the unit on my y-axis. However, that changes dramatically if you make the switch to a main memory system. And now, all of a sudden, logical logging and all these intermediate things are not that expensive anymore. They all sit in that, basically squashed into a small region on the y-axis. And that is why main memory systems, you will see more often logical forms of logging, whereas on disk systems, it's more on the physical side of logging. Yeah? You will understand that better once we go in the full algorithm of how to recover the data. But just to keep in mind, what I'm explaining in the following makes sense if your storage system is relatively slow. If your storage system is relatively fast, you can more and more go into logical logging. It's okay to allow for fast recovery. So here's an example where you, for logical logging in main memory, here you basically just store the invocation parameters of the stored procedure in the logs. So I'm not sure whether you recall stored procedures. In SQL, you can prepare a statement. That's also used to avoid SQL injection attacks. Basically, if you have a statement like that, like updating a certain table and setting a certain attribute to a certain value, there's some spaces missing here. So basically, you have here 3 parameters. And what you could do in a situation like that is that you just pre-optimize that statement by preparing it. There's an extra command for that. And in the log, you just keep the ID of that specific query plus the invocation parameters. That's what you see here. Yeah, so that's 0 is the ID of the query, and those are the invocation parameters. That is super efficient, of course. Yeah? Then you don't have to store much data, and basically, as long as you also keep the dictionary, of course, when going through the log, you basically join whatever is in the log with a query dictionary on the query ID, and then you can recover the database state. So that's a high-level form of logical, yes, logging.
I have a from before on the physical login, since we have the spot where we will replace them. So why don't we just say
You mean to the slide before?
in the physical
Yeah,
version of it?
here.
Yes. Why do we need to keep the
Mm-hmm.
KE and not just?
Yeah, I don't know. Someone has an idea? Yeah? Yes. You can revert back with that. You undo changes you did. It's human transaction that didn't commit, did the change, then aborted, or power failure, and then you have to go back. So physically that means you have to go back to the old state of those 2 bytes, and that's exactly that information.
But if it didn't commit, then we didn't change the store. So
No, it could have been that the page was written out. Okay, I see what you mean. No. The world we are in is really like, maybe we go back to that, what's a good example of explaining that? I think that's a good one, here. I know that was a violating thing, I have to find the right example here. I think that's a good one. So what may happen is, this is respecting write-ahead logging. Yeah? So it was first written out there, and then it was written out to the store. But I didn't tell you whether that change was done by a winner or a loser transaction. Yeah, if it was a winner transaction, that's fine, it's in the store, it should be there anyway. But if it's a loser transaction, so a non-committing transaction, we must remove it from that page later on. Because the transaction didn't commit, so it mustn't make anything durable. So this change, if this was done by a loser transaction, has to be removed. And with that, and then you can do that using this before image in the log entry.
So we don't wait for the transaction to commit in order to write the data to the tab.
Yeah, it's okay, good. Yeah, it's fully orthogonal. Yeah, the store and the database buffer, they do what they want. The store writes out dirty pages, no matter whether on the dirty pages are changes from losers or winners. Yeah, so the store on disk may be in any state, really. Anything may happen. Huh? Yeah, good question. Okay. Okay, so we were in, okay, here, that was logical logging. No? So with that, now we are prepared to really explain the method I'm up to explain, and that's called ARIES. That was invented in '92 already, and then many database vendors picked similar methods or exactly the method up and built it into their systems. And the algorithm works in 3 phases. So there's an analysis phase, that's the first phase, there's a redo phase, and there's an undo phase. And the idea is really, so assume again, so that's depicted here, that's this dotted line, that's our log file, this is the first entry in the log file, this is the last log record persisted in that file. Yeah, and then the crash happened. That also means the main memory version of the log file might have had more data, but we don't know. That's really lost. Yeah, we can only look at the data, at the log records that were persisted in the log record. Yeah? We don't have anything else. So at this point in time, the crash happened. And now the algorithm runs in 3 phases. The first is the analysis phase, starting from the first log record, reads it sequentially from beginning to the end. Then I will explain in detail what the analysis phase does, if there's separate slides on that. But basically, it determines certain metadata and information that allows the system to do the redo and undo phases. Redo means now I start somewhere in the middle of the log, could actually also be the beginning of the log, but hopefully let's start somewhere later and read the log entries and reapply all the changes. So all changes that were done or should be done to the store. So any operation in the log doing a change like insert, delete, update is reapplied to the store, independent of whether it's a winner or a loser operation. That's very important. You might think, and some methods do that, well, why would I reapply also the loser transactions because their changes shouldn't be in the store anyway? not in ARIES. ARIES redoes everything. And the answer to that is it's more efficient and it's actually easier in the algorithm. And then there's a third step. In the third step, we do a backwards pass over the log to remove changes from the transactions that didn't commit, that were running at that time but hadn't committed yet. So their changes are removed in the undo phase. Those are the three phases. And we will look at that in detail and also with some extensions. So I will explain the most simple version of that algorithm for now and then build upon that. So there are two important structures we have to keep. One is the transaction table, TT, and one is the dirty page table, DPT. And the semantics of those tables is really easy. So the transaction table only tracks the non-committed transactions. So only the transactions that are currently running in the system are stored in that table. Yeah, so if a transaction commits, it's removed from that table. If a transaction starts, an entry is created for the table. So you look at the table, you know those are the ongoing transactions in my system. That's the transaction table. And then there's the dirty page table that tracks all the pages and their earliest points in time when they may have become dirty. Yeah, so those are your interesting pages you may want to revisit in the redo phase. Those are pages that are possibly out of sync with where they should be version-wise. Yeah? We will look at that in detail later on. So you see there are certain fields here. Here's the last LSN, and here's the recovery LSN field. So of course I have an ID concept, so each transaction has a unique ID, transaction ID, each page in my system has some sort of ID, however you represent that, doesn't matter, just has to be a key. And here the last LSN has a semantics that is a log sequence number of the most recent log record seen with this transaction. So log sequence number, you organize, so if you organize your, maybe I can write it down here. How do I write it down? Maybe we can show it here. I think that's a good place to show it. So if those little dots are your log entries here on that slide, each of those log entries has a certain offset in that file. Right? You have a byte offset. If you write a file, you have a certain, you typically seek to an offset and then you write something. So each log record sits at a particular offset, and that is a key. That's a log sequence number. Yeah? Because if you go to that position, you know, okay, that's a log record. Yeah? It implies that not for each and every possible integer you have a complete log record, but basically when you look at the log record, you know its first byte, its offset, that is a log sequence number. So you have a natural key concept in such a log record that you can use in the algorithm. You can also organize it differently. You can also organize it along relational terms. You could do something like that, yeah, where you whatever do an append. If you say, okay, that is my log, and I write it down as a relation of some sort, like here in that example, and then I write LSN log sequence number, underline it, that is my key, and that is the actual entry. Yeah, then you would start with 0, there's an entry, and then whatever, 42 an entry, 78, 175, whatever. Yeah, so that would be the same thing. Yeah, I'm just saying there's a key concept that's called, or a key that's called the log sequence number, which allows you to address those log records, and the most natural thing is to use the offset in that file. Okay. Where am I? So no, we're here, actually, the right. Okay, so last log LSN. So here, what you store is the last LSN, so the last log record that was written in the log and performed for a particular transaction. So at all points in time, you can look at this. You can look at this table, yeah, and see what was the last transaction, the last log record executed for this particular transaction 3, for instance. In the dirty page table, and the more log records you process in the algorithm, you will change those entries here. They will change. In contrast, in this table, once you inserted a particular page, this entry here, the recovery LSN, will never be changed anymore. Because there are special cases where it will be changed, but in the easiest version, it's not going to be changed. So the main semantics is what an entry like this is saying. So for page 3, the earliest possible log sequence number that should be reconsidered or that may have caused a problem or may not have been applied is 42. So you know all log entries that are smaller than 42 you can ignore. In other words, that page 3 is at least in that specific version as of before. So that is the first entry that may have led to the page becoming dirty. It's really complex. Yeah, so basically it's, how could you phrase it? You could also say that's a to-do list. Yeah, so for each of those pages, you want to make sure that all of the changes have been applied. And this number tells you, okay, that is the first log record that I should really inspect to make sure that the change reflected in that log record is applied to the page. Yeah? The extreme case would be, okay, they have zeros everywhere, 0, 0, 0, meaning, yeah, whatever the page, all of the log records have to be applied, have to be checked whether they were applied on that specific page. Yeah, and again, we make these assumptions that any, as told you before, any page may contain actions from losers and winners. So in particular, if you write out a dirty page, it may be that on the database store, in the file persisted, you have changes from winner and loser transactions on the same page. But we will be able to handle that. So what are those log records? In detail, they look as follows. So we basically will see 3 different types of log records. And they all share those fields. So one is a previous LSN. That's just a pointer to the previous transaction. So the previous log sequence number of this transaction. So yeah, in every log record, you keep the transaction ID, you keep the type of log record, but you also have a backlink to the previous entry of this transaction that was written in the log. Yeah, that's basically all that's happening here. And that gives you a linked list over all of the log sequence numbers for all of the log entries for one particular transaction. We will see a very detailed example in a moment, then you understand what that means. And yeah, and then the major thing we have to understand are those update log records. So again, transaction ID, the type, it's an update. We have the previous LSN pointing back to the previous entry. We have here the page ID, we have the redo info, and we have the undo info. Yeah, so this page ID already implies that this is not logical logging, what I'm doing here. Yeah, this is at least physiological logging or physical logging because I'm specifying a page. If it were logical logging, there shouldn't be a page here. Yeah. So there's the redo info. So that's the information how to redo the change. And we do that physiologically. And there's the undo info, that's information on how to undo. So there are different variants of the ARIES algorithm. The state of the art is to do logical undo, physiological redo and logical undo. To simplify matters, I will assume everything is physiological. That's okay to understand the concepts. It simplifies it a bit, but that's okay. So with that, let's look at the concrete run of the algorithm. Then you see all of these data structures in action. So here's the database buffer. I have 2 pages, 42 and 46. On those pages, I have some data. So I have here, I don't talk about tuples for the moment. I just say there's a variable A that's set to 77, B is set to 55. On page 46, there's a variable C that's currently set to 22. Note that in addition, on the header, so basically a page in the database store is separated into header and body, like on an HTML page, basically. Here, on the header of the page, we can keep metadata for that page. We touched that briefly before when talking about the store. I told you, hey, you could compute a checkpoint on the page and store the checkpoint on the header of the page, yeah, to have another means of error correction. But what disk-based systems also do is they keep their log sequence number. And the idea here is that is the log sequence number of the log entry that was applied last to that specific page. In other words, that's the version the page is in with respect to the log sequence numbers. Yeah, do you see that? That's the versioning information here recorded. So currently it's saying dash, that means null, so the log is empty anyway, so there's no valid log sequence number. But now if I fill it, if I do this, maybe let's ignore this stuff for the moment. Let's ignore that and just make one run. So assume the first entry here, I gave it an artificial ID, it's first log entry 1. It has no previous entry. It's transaction 1. It's an update record. It's affecting page 42. It's increasing A by 1. The undo operation is decreasing A by 1. So basically, when you look at the page, previously it was 77. Now it's increased to 78. I do that at the same time. Again, with write-ahead logging, you can do it first in the log and then in the store. I do it at the same time to simplify matters. And then you see what happens is, it's not only that you change this to 78, but you record this log sequence number on the page. Yeah, so far so clear? So the versioning information is kept on that header of the page. And now you continue. There's a second change operation, again affecting page 2, page 42. You increase B. Yeah, you also set the LSN to 2. Yeah, and so forth. Ignore everything on the right for the moment. And so forth. Here's another update operation now on page 46. So we have to increase this one from 22. We record the log sequence number. So that's how the log is, or how the log is applied to those pages. Again, 42, set log sequence number, change those values, and so forth and so forth. Yeah? Yeah, that's just what happens on the pages and what happens in the log. So let's look at these ARIES tables, what they are doing. So again, I start from scratch. The first update record comes in. Well, I have a transaction 1. So this is not a commit record, which means implicitly the transaction is running. You could also write a begin log record to signal that I started a transaction, but that's not necessary. Every time you encounter a transaction ID that's not recorded yet in your transaction table, that's implicitly a begin transaction. Yeah, you're starting a transaction. So you don't have an entry for that, so okay, you make an entry here. Yeah, so the last LSN executed was 1, this one. The transaction ID is also 1, yeah, it's this one. Okay, and what do you do in the dirty page table? Well, you're touching 42, and the recovery LSN is 1, because that's the first LSN where it possibly became dirty, yeah, this LSN. That's what's done for the first log record here. Now the next record, the next change operation, next update on that log record comes in. So it's the same page, but a different transaction. So it's transaction 2 operating on the same page, so you have to do another entry here. Notice that this doesn't change. As I told you before, those values, those recovery LSNs are in normal operation never updated. Yeah? So it stays to be set to 1. Yeah? Next entry comes in, an update operation on page 46 for transaction 2. Well, transaction 2 was already in the transaction table, so we don't do a new entry. However, we update this value, the last LSN, to the last log record we processed for that transaction. It's 3. Yeah? And we touch the new page, 46, for the first time, so we have to make an entry here in the dirty page table with the recovery LSN of the last log end record. That's 3. Yeah? So far, so good. Next entry comes in. So this is affecting page 42 again. We've seen the transaction 1 already, so no new entry. We already have the entry here. We do an update on page 42. Well, it's already in the dirty page table, no change here whatsoever. So no change in any of the tables, except, of course, that we have to change the last LSN in the transaction table. That's the last log treated for transaction 1. Next entry is a commit for transaction 2, which means we remove it from the transaction table. Yeah? Because it's not an ongoing transaction anymore, it's now committed, so we remove it. Semantics of transaction table is just the ongoing transaction, so we remove it. Yeah, so far so good. That's the log in normal operation. So we will also need a third type of log record, and that's called the compensation log record. And that becomes important during recovery. And the semantics is a bit weird, but you will see it makes sense. So again, you have this previous LSN and transaction ID. You give it a type, that's compensation. That's a page ID, because we are physiological, as I told you. And then there's this weird field, redo the undo. And there's the undo next LSN. That's the next transaction to be undone for this transaction. But the interesting thing is this one. Just swallow it for the moment. You will see how that works. The major takeaway is this is undo information that was pushed to the redo part in the algorithm. So what that means is those records are being written in the undo operation. However, if you crash again, you will execute them in the redo information. And let's look at an example because it's really otherwise hard to comprehend. I wrote it down again, here's the semantics, but when you see it on text, you feel like, huh? What the heck, yeah? So what I just told you is it's created for each operation that was undone during recovery. So some operation from a loser transaction was undone, and well, you undo something, you modify the store, well, you have to write a log record. But that's not a log record from an original operation. The stuff the user sends to the database system, but that's a change operation performed by the recovery algorithm. You have to do write-ahead logging, even for those algorithms. So there's an artificial log record being written for undoing changes. And that log record is called a compensation log record. Yeah, so the algorithm writes log records to the log, not the user. And yeah, the idea is in case of a repeated recovery. So repeated meaning, I mean, it may happen that during the crash, you crash again. Why not? Yeah, it could happen. Then you still have to be able to cope with those situations. And the question is, how would you do that? Yeah, so that looks weird, but it makes sense when we look at that. So here's a visual representation of how those log records could be linked. So I have two transactions here. One is the yellow transaction, one is the green transaction. We have a I killed the legend here, right? Anyway, so the green is one transaction, the yellow is one transaction, and let's go back. Here, that's the original situation, and that is normal operations. Those are just the update records. Each of those bubbles is an update record. That is the first of transaction green, and that is the first of transaction 2. Yeah? That's the second of transaction green, and so forth and so forth. And you see the backlinking. Yeah? Each log record has a pointer back the previous LSN, and if it's the first log entry for transaction, okay, that's pointing back to null. Obviously, the same holds here for the first entry of the yellow transaction. That's a normal log, yes, you would see it. There are update log records and there are commit log records. Now, if you crash, as I told you, you have to undo the loser operations, and then basically you write those extra log records, and they are called compensation log records. That's explained here. So basically 7 prime is undoing whatever 7 did to the store. Yeah, that's basically the inverse of that. And then 6 prime is undoing whatever 6 did to the store. And then of course there will be a 2 prime undoing whatever 2 did to the store. Yeah? And green is not undone because I'm assuming that green committed in this example. Yeah? So the log may look something like this actually. Okay, yeah, let's look again, let's make an example, let's extend our example. Let's assume we crash. So that's where we were in before. So we have a crash after log entry 5. So basically, this is what I find when restarting the system. That is my log. So transaction 1 is a loser transaction. Why? Because there's no commit entry in the log. Transaction 2 is a winner transaction because there is this commit entry. And committed, there's an entry in the log. That's okay. So although the changes of transaction 2 should be persisted, changes of transaction 1 must not be persisted. So what do we do? After the crash, you start undoing the last action performed by transaction 1. So that is this one here, right? This here. Yeah, that is the action you need to undo for that transaction. And you see, you had this redo information, you had the undo information. Now it's only the undo information. And why isn't there the standard redo information? Do you have an idea? It's just the undo information, and that's executed in the redo phase. Yeah?
Because the data, because the pages are already up to date.
With respect to what?
Are these pages, this page 42 and 46, are they already written to this with the MS
No. Let's get to think about the semantics of the redo and the undo information. You keep the redo in order to be able to reapply it to a page. You keep the undo information in order to be able to undo the change for a loser transaction. Now I have a log record that only has the undo information, however it does it in the redo phase. Huh?
Why would we need the redo information if it crashed and we just undo what we did? I see no point in having the redo information.
Yeah, this is the redo information. That's now the redo information reflecting an undo. I think it's really, yeah. Yeah, you see when you look at the operation. Yeah, so it's b plus b increased by 1 in the log record 4, b decreased by 1. So redo and undo. Now it's only decreased by 1. That's semantically the undo, however, executed in the redo phase. Yeah? Yeah, why don't we want to undo that? Yeah, right, exactly. Yeah, you will never undo what a compensation log records action was intended to do. There's no other levels undo if you want to do it. I mean, compensation records are written while undoing operations in the database store. And what the compensation log record reflects is exactly that action of undoing that action. Yeah, but you never want to undo this. Sentences get more and more complex. Yeah, you will need a few runs in the lab on Friday to fully appreciate what it is. Yeah, but basically what that means is let's look at it like that. So if you have a standard update record, two things may happen: you redo it or you undo it. Hence, you need both of that: the redo information and the undo information. A compensation log record is never undone. It's only be redone. Yeah? And redoing semantically means you repeat your undo operation. That is what a compensation log record is doing. You repeat it for whatever reason on the store. Yeah, that's what she said. Basically, there's no need to undo a compensation log record. Yeah, this ARIES. I mean, it's obviously. I mean, I've been explaining this for 10 years now, and I was. It's pretty like reading a book, like a big novel where you have like 100 characters, and you first have to digest. Oh, those are all these characters, and that is how they interact. And finally, on page 632, you get an idea on what the book is about. Yeah, it's a little bit like that. Yeah, and keep in mind, this is the easiest version of the algorithm you will find anywhere on the web, I guarantee. Yeah? And typically it's much more complex, yeah. But it requires a little bit of, hey, okay, there is this structure, you just have to accept it, there's this, they're doing it like this. Eventually it will do, I understand. Yeah? So it's a little bit like that. Yeah? Okay, so here's our compensation log record. Yeah, and then there's another crash. Yeah, so after the second crash, we continue. But then you see there's no new compensation log record being written. So basically what the system will do is it will execute all of this in the redo phase up to here. And then when it continues undoing the actions of that transaction 1, it will write out a new compensation log record. Yeah? That's basically the idea of that. Yeah, and once you're done, you remove it then also from that ongoing transactions table. So let's look at that in more detail. So what are the tasks of those 3 phases along the lines of those structures? We had the high-level description before, but now let's go into detail. So analysis phase, you reconstruct the dirty page and table and the transaction table to reflect the state at the time of the crash they were in. So in other words, when you run the ARIES algorithm, when you keep writing log entries, you keep these, you keep the DPT and the TT, make your entries, remove entries and stuff like that. And the goal of the phase is to reconstruct those tables. I want to know what was the state of DPT and TT at the time the system crashed. That is the task of the analysis phase. And the second important goal is to compute this min dirty page LSN. That is the earliest log record that might have dirtied a page, might have led to a problem on the store. So if you go back to, where's that? Maybe switch back to the high-level overview. Here. So you see it here. So analysis starts here, does a forward pass. So once you're done, you have the DPT here. You know the DPT as of the time of the crash. You have the TT as of the time of the crash. And you know this point. So that is the earliest possibly dirty page in the system. How do you compute that earliest possibly dirty page? With which operation? We can go to our example. Let's look at this one. What is the earliest possibly dirty log sequence number that you would have to consider for the dirty pages? How do you compute that with these structures? Yeah?
Check the pages that the operation changed and then go to the DPT table and then just get the number from there?
Yeah, okay, goes in the right direction, but a bit more precise. So we learned the analysis phase reconstructs the DPT and the TT. So you have the version as of the crash of the DPT, however that table looks like. And you have the transaction table. Now you want to know what is the first point in the log, the oldest log sequence number to consider for treating dirty pages. What is the oldest?
It's in the table.
Yeah, but how exactly? What's the operation now? There's a word for it, right? It's in the table. That's correct. Absolutely correct. Let's propose a minimum of the recovery LSNs, okay? That's the oldest, right? The oldest LSN available in that table. You didn't say minimum. I don't know why. I think you meant the right thing. Yeah. So the minimum. Here we go. Yeah. That's basically, and from that, and now we go back to high-level description here. Yeah, so we're here. This is what we computed. Now you know where to start the redo phase. What do you do in the redo phase? you go through the log, starting from this point in time till the end of the log, and you repeat everything. Yeah?
But aren't these actions state dependent? Like,
Yeah.
for example, update would depend on the previous state.
Yes. Yes.
From a
Yeah. 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 Very good. You check. Actually, you see it in the pseudocode. You can't blindly apply this stuff. For physical logging, it's not a problem, but for physiological and logical logging, it's a problem because you may only apply it if it hadn't been applied before. Yeah, you're absolutely right. You will see in a moment how that works. You can use the version number basically on the page, on the header. Yeah. When they see the version, oh no, it already has that version. I don't have to do that. Oh, it doesn't have the version. Oh, I better reapply it. Yeah, that's the trick. Yeah.
Analysis phase. How do we erase something from the GPT?
How do we erase?
Yeah, my problem is isn't always the first sequence number in the logging also in the GPT because we don't erase something and we don't know where the state of the storage exactly is.
You're saying, okay. So whenever you touch a page for writing, you would insert it into the dirty page table and that never gets removed, right? Yeah, that's kind of a stupid algorithm I just explained, right? So how would you remove it from the dirty page table? That was your question. Has someone an idea? We can go back to this example here. So how would you remove it? Absolutely valid question. Yeah.
When we commit and persisted to disk.
But when you what?
When we commit and persisted to disk.
Now be careful. Committing and writing out, completely different stories in a database system. It's typically, very old algorithms did it like that. But yeah?
I mean, here by writing out, you delete the dirty page thing.
Yeah, but hold on, whatever. Keep in mind what you're about to say. You're writing out the dirty page. What does dirty mean? It's in a different version in the buffer than on disk. If you write it back from the buffer to the disk, it's not a dirty page anymore by definition. You remove it from the dirty page table. Yeah? Now second part.
In the analysis phase, you don't know what's exactly written on the storage. So I don't know if there's a crash after 4 now.
Yeah.
Can you go one further with the commit?
Like that?
Yeah, like that.
Mm-hmm.
Now, when there's a crash after the commit,
Mm-hmm.
we don't exactly know if. Oh well, I see my point. Never mind.
There's a little assumption here. Okay, do you see the assumption I'm making? I think you got the idea why it works, but there's a tiny little nasty assumption I'm making. And it's kind of important. So one is the log sequence number. That's the version of the page. So I recorded it here. So I didn't record it for the commit because it doesn't make a difference actually. But for the last update log record on page 42, for instance, or on page 46, the LSN3, that tells me that is the version the page is in. In other words, when I later revisit the page, I can make a decision, do I have to reapply the log record, yes or no? It's very important for logical and physiological logging, for physical not so much. However, that assumes that the change I do on a page is atomic, is transactional. Because if you just change the LSM, but not the data underneath or vice versa, anything in between, you're in trouble, unless you are in physical logging. But for all logical variants, it's a problem. See what I mean? That's the hidden assumption. Transactional change of the page. Otherwise, it doesn't work. Yeah? And if you blew up your page, that may also happen. That may be that you end up in a database system where the page cannot be recovered. Yeah? You have no consistent version of the page for whatever reason. Then there are extensions to the algorithms. They're called media recovery that allow you to selectively get back the page and play it forward to the right version. That can also be done. But for the normal algorithm we're looking at here, it's really important that you have that version number and that the changes on the pages are done atomically, transactionally. Otherwise it wouldn't work. Okay. So where was I? No, pseudocode I wasn't. Okay, here I was. Okay, so we repeat all actions, no matter whether the transactions are winners or losers, and we also repeat all the compensation log records in the redo phase, even though semantically they reflect an undo from a previous undo operation. For a previous crash. They are compensation log records are created in the undo phase of a crash. However, they are re-executed in the redo phase when recovering. So we repeat everything. And this paradigm is called repeating history. I wrote it down there. So it's called repeating history. So after the redo phase, your database store is in the same state it was in as of the time of the crash. Yeah? You now know all my pages, at least in the database buffer, are in the same state as of the crash. And now the only thing that remains to be done is you repeat, you undo the actions of all loser transactions. So how do you determine the loser transactions? Which are your loser transactions?
Every transaction that's not connected.
Yeah, and how do I get that? Huh?
Where's the commitment in the log?
Yeah, that's true. Yeah. Yeah, it's just whatever transactions are still in the transaction table after the redo phase. Yeah. So that's the ones you have to look at. And whenever you undo an action, yeah, however that works in detail, we will look at next week, I suppose. You write a compensation log record because you changed the store. Yeah, here the undo phase applies changes to the store. You have to do write-ahead logging. You have to write a log record, and that log record is called a compensation log record. Yeah, that's a high-level idea of the algorithm. So I think you have enough to digest. So we will start with that in the lab. Actually, there are not so many. There are a couple of more extensions. We will dive into that next week with a pseudocode. I just wanted to remind you that I'd like to ask you to fill in the course evaluation. We have two separate links. It's electronic this time. Here you see it in our CMS lecture and tutorial. Please fill that in. It's really helpful for us to understand what you liked or whether there are things we can improve. So please fill that in. I'm not sure what the deadline is. Probably it's on the questionnaire. So thanks. See you on Friday.